it setting and recommend? For some reason on my desktop, I have to set up, like, in order to be able to run programs and do like arguments in the command, I have to do it, set it up every single time I want to do it. I could do it on regular hardware.
Yeah, it does. It does make sense. Okay, that works. All right. So it is. I'm recording. I'm streaming right now. So everything is going to be recorded. Um, so let me first go over the program itself, and then we'll go ahead and look at how it runs. Okay. The program is called tree.c, and okay, I'm going to have to change my glasses. All right. So the first few lines. Let me display the line numbers. Okay, so when you look at lines, line 1 is easy. Okay, all we are doing is to bring in standard integer.h so that u in 8 underscore t is actually defined. So that's the job of line 1. Lines 2 to line 7 is the definition of the structure. Okay, line 4 is pretty easy to understand. We have a member called value, and it is an unsigned 8-bit integer. So that one is easy. Line 5 and 6 may look confusing, but they're L and R, each one is a pointer to a struct node. And that is okay in C and C++, because most people would think that this is not possible because we are in the definition of struct node. How can we use struct node? Well, the answer is they're pointers. Now, if L and R are actually struct nodes, then we have a problem. Okay, but they're not. They are pointers to struct nodes, which means L as a member is storing an address of a struct node. Now, is it the address of the very same struct node that it is in? Maybe, maybe not. It doesn't have to be, as we will see later on, the initialization says, it just has to be an address of a struct node. Okay, so do we have any questions about lines 2 to line 7, how we define the structure? Yep.
How much space will they take up?
In TTP-ASM, every address is only 8-bit wide.
Yeah.
So you can just allocate 1 byte for L and 1 byte for R.
Right, and so then the size of the whole struct node is 3
Yes.
bytes?
Yep.
Okay, thanks.
So I'm going to ignore traverse for now, even though eventually that is the important part. So I'm going to skip to line 27. Line 25. Line 25 is an external, definition, which basically is just telling the compiler and say, don't panic when you see these names. Okay, I know what they are. N1 is a struct node, N2 is a struct node, and so on. So don't panic, because we have some forward references from line 26 to line 30. So moving on to line 26. So line 26 is declaring a global variable called N1. Itself has a type of struct node, and this is how we initialize it. In other words, I'm just manually initializing N1 as a struct node, where the value is 5, L is the address of N2, and R is the address of N3. So does that kind of help understand what L and R really are as members of the structure? They're just pointers. They're just addresses of another struct node. Are we good? Yes? Okay. But when you look at N2 all the way to N5, some of those L and R values are zeros. NULL, null, is a fancy way to refer to 0. That's all. Null is really just 0. So instead of pound including another header file just to get null defined, I'm just saying 0. Are we good so far? Yep.
Same as null pointer?
Yep. So 0 is a null pointer. So when you look at line 26 to line 30, that should remind you of certain things that you see in question number 3. So question number 3 in assembly code, that's the assembly code way of implementing in C line 26 to line 30. Are we good so far? Now, the assembly code in question number 3 can also be copied and pasted into the assembler, so you can actually see what kind of byte sequence it compiles or assembles to. That would help you understand what it really is saying too. Are we doing okay so far? Yes? Okay. So when you look at N1 to N5, okay, it is defining, what we usually call a tree. So N1 is quote unquote the root node because nobody else is pointing to N1, so it is our starting point. The left of N1 is N2, the right of N1 is N3, and then we look at N2. N2 has a value of 3, which is not displayed in the picture, but it does have a right node of N4, and then N3 has a left node of N5. Okay, so that's kind of what the quote unquote tree looks like. Are we doing okay so far with this? No? Yes?
I don't get what you're referring to with nodes and tree. Like, I get the structure, but I don't get why it matters left, right, hierarchy. But
Okay, this is the L member.
right.
This is the R member. So the L member of N2 does not point to anything, so it's not displayed. But the R member does point to N4. So this is the L member of N5.
Yeah.
So it's what you see on the whiteboard is just one way to visualize, the how the structures, how the nodes relate to each other. Is that okay? All right. So the main program, you will need an array that has 5 bytes. You will also need a local pointer. So you have to first initialize the pointer to point to the beginning of the array, and the array must have at least 5 elements so that we can store those values. And then when we call traverse with the address of N1 and also the address of PTR. Now PTR itself is a pointer, so the address of a pointer that's why it has 2 asterisks, because PTR itself has 1 asterisk already. So when you refer to the address of PTR, now that's why we have 2 asterisks when we get to traverse. Are we good? Okay. So let's now take a look at traverse. Traverse is not long, okay, but it can be confusing. So the logic of traverse says, if pointer is not null, this is what we do. But what if you give me a null pointer? Then I go like, nothing to process, okay? You didn't give me anything to process, so I'm not going to process anything. So that's what line 11 is for. Line 13 says, okay, well, let's check out the left-hand side, okay? If the L member of the structure that pointer points to is non-null, okay, fine, we'll process that. How do we process it? Recursion. We just pass array along, and then what we do is we say, okay, let's process the L member of the structure the pointer is pointing to. Are we doing okay so far with that? Okay. And when traverse returns, this can be confusing. I understand that. So what you can do is to separate line 17 into 2 different statements if you want it to be absolutely clear. So let's go ahead and do that. So I'm going to separate it into 2 lines. Okay. The first line is going to do just that. Okay. Because the plus plus means do the increment after everything else is done. So the second line really only has to do, let's see, this part here, and nothing else. Is that okay? So let's go back to line 17 and find out whether we understand what line 17 is trying to do. Because now, I just cleaned up 1 pair of parentheses that is not needed. This pair is not needed either, okay? So we first look at the right-hand side of line 17 the way it is now. Does that remind you of something that we did today? Hopefully, right? So the approach that we used today would work on the right-hand side of line 17 pretty easy. Okay? The left-hand side needs to access array, but then we are not interested in array. We are interested in what array points to. But then we don't want to store something to what array points to. We want to store something to to the location that was pointed to by whatever was pointed to by array. So it's really just a matter of counting dereferencing. The last dereference has to be a st because we are storing. This is on the left-hand side. But then the other dereferencing will be using ld because that's the only other dereference that we have. Is that okay? So you have to let's count. we have to get to the address of array first. That's without any dereferencing. Then we get to array itself, 1 dereference. Then we get to what array points to, 2 dereferences. Then we store to what that thing is. That's our last dereference. But the last dereference is not for reading, it is for writing. So we should have 2 LDs and 1 ST. Okay, I'm giving you as much information as I possibly can without doing the actual code for you. Okay, is that okay so far with the left-hand side of line 17? I hope so. Are we good? Okay. So on line 18, it looks confusing, but if you look at increment, in a more traditional way, then it is not as tricky anymore. Because that's basically what line 18 boils down to. You get to what array points to, grab that, add 1 to it, okay, and then you store it back to where array points to. We should be able to do this because the swap subroutine has something that looks like this. Okay, we have a parameter, and we are storing to where the parameter is pointing to. Are we good so far with line 18? So borrow code from the swap subroutine for line 18. And then on line 17, you can borrow code from what we did today. Are we good so far? Okay. So when this is all done, when line 17 and line 18 are done, then we move on to the R member of the structure that is pointed to by pointer. If that is not null, then we traverse that side as well. So we pass R member of the structure pointed to by pointer as the first argument, and then array is just passed along by itself. So we are really just passing whatever was passed to me and just pass it along in the recursive call. Is that okay? More or less?
More or less, but I'm not sure what we've accomplished by doing this.
Okay, so what it is accomplishing is if there is a left-hand side, it will go process the left-hand side, then it will process itself, the node itself, and then process the right-hand side. So what does processing mean in this case? Line 17 and line 18 is quote-unquote the processing. All it does is to retrieve the value of the node, append it to the array that is ongoing, and that's it. That's what it does. Okay. Okay. So this code does compile and it also runs. You can do it in code blocks. You can do it in regular GCC. You'll do it however you want to do it. I have already compiled it in GCC, so I'm running it in GDB right now. So what we'll do is we'll put a breakpoint on line 41. And let's see, we'll put a breakpoint on traverse itself. Okay, there we go. We run the program. It stops on in main. This is the first call. So the first call to traverse has n1, the address of n1 passed as pointer, and it also has the address of pointer. I know it's confusing because I used the name pointer in main too. But this is basically the array. This is the beginning of, it's the pointer pointing to the beginning of the array in main. Okay. So let's go ahead and look at main again. So if you say, what is array A? Okay, print, I may not be in the right context. BT, okay, I'm already in traverse because I stopped in traverse. So let me frame 1 first. Okay, I'll go back to the main frame, and then we can print A. And we can print the address of A. You cannot see it. So the address of A ends with a E0DB, which is not what you see over here. But the main subroutine has another variable, which is pointer. So when you look at the address of pointer, you cannot see it, but I can tell you that it is E0D0, which is this guy here. So what we're passing to traverse is the address of pointer as a local variable in main. And you can look at the source code on your side because I sent you the code already. Now back to frame 1. Okay. So back to frame 1, we are at the beginning of traverse. So when we single step, the first thing we do is what is the L member of the structure the PTR points to. Now, in a debugger, you can do this, okay? You can do this. I know you cannot really see, the numbers that are in dark blue, but it doesn't really matter because what we know now is pointer inside traverse is pointing to a struct node. The struct node has 5 as its own value. L is pointing to N2, and then R is pointing to N3, which is consistent with what this picture is showing you, right? Now, because L is non-null, okay, when we single step, it will do a recursion. So when we do this recursion on line 15, it is passing L, which is really N2, the address of N2 along, and we'll traverse that also. So when we single step, now we're getting to the second invocation of traverse. In GDB, and also you can do this in code blocks, if you run the command called bt or backtrack, you can see that we have 2 invocations of traverse already. This is main. Main is calling traverse. Traverse is calling traverse again. But the second invocation of traverse is using the address of N2 as the pointer, and then we can print it. Okay, we can now print PTR, which is the structure pointed to by pointer, and you can see in this case the L is a 0. Okay, it's a null pointer. So when you single step, the conditional statement is going to say false. Okay, because the L member of the structure pointed to by pointer is null. So it's not going to do another recursion. And what it will do instead is to go to line 17. Line 17 says, go ahead and retrieve the value of the structure pointed to by pointer, which is 3 in this case. But where are we storing it? That's the question, right? That's the $1 million question. The $1 million question says, okay, what is array? Okay, you cannot see this, but array itself is pointing to the local variable PTR in main. And what is that thing pointing to at this point? How did I initialize PTR in main? Look at the code. It's pointing to the beginning of the array A, right? So when we store, okay, using line 17, when we store 3 to the location that is pointed to by the pointer, which in return is pointed to by array, we are actually storing to the first byte of array A in main.
So you're filling out an array with each
Yes, we are filling in array A of main as we traverse the nodes in the tree in a in-order fashion. Is that okay? So when we single step this, okay, now I have just single stepped line 17. So the question is, how do we check? Is this 3 really stored in array A, which is a local variable in main? Okay, so you can check that. You can use BT again, okay? This is backtrace, and then you can say frame 2. So frame 2 is basically saying, okay, I want to look at things from the perspective of main. So now we are looking at things from the perspective of main, which means I can now print, okay, tell me what is the first element of array A of main? And that's 3. So we are filling in the array A, of main step by step. The pointer that you pass as the second parameter to traverse is the thing that is keeping track. What is the next location that I can store? What is the next location that I can store? So when we do a frame 0, which means we're switching back to frame 0, which is exactly where we are now at this point, the next statement that we are executing is line 18. What is line 18 doing? Well, we have just used the location that is pointed to by a pointer that is in return pointed to by array. That location is used. I need to move on to the next location. So the way we advance the pointer which is in return pointed to by array, this is what we do to advance the pointer. Okay, so let me single step this. Okay, so this should have advanced PTR as a local variable in main, so that it is now pointing to the first element of array A in main. Does that make any sense? Okay, so how do we check that? Same thing. Backtrace, frame 2, Okay, now that we are in main, we can now ask what is PTR. So we can ask what is PTR. You cannot see this at all because it is really dark, but it says E0DC at this point. Okay, but at the same time, you can ask what is the address of the first element of A in main, and it says exactly the same thing, E0DA.
Wait, you said DC and then you said D.
DC, they're both DC. You can also do this, okay? If you really don't care what the value really is, you just want to see if they are the same, you can do it this way. You can compare pointers, and it says, yep, they are the same. So that's basically what traverse is really doing. It is doing an in-order traversal of the tree, and then it is storing the value of the node into the array and moving on the pointer to the next point. Are we doing okay so far? Okay, so let me go back to the tree, and this time we'll actually put in the values. And you guys can help me. What is the value of M1? I think that's 5.
5, and then 2 was 3, and 3 was 10, and 4 was 4, and N5 was 9.
Okay, so because we're doing in-order traversal, that means we'll do everything on the left-hand side first, and then we get back to ourselves, do the operation, of my own node, and then perform the operation on the right-hand side. Okay, so the order of doing this is it will first arrive at N1, but because N1 has a left-hand side, then it will go like, okay, I cannot process the 5 because I got the left-hand side. So move on to N2. N2 says, I don't have anything on my left-hand side, so it'll process the 3. So array A is going to have a 3 at this point. And then we'll go to the right-hand side of N2, which is N4. N4 has a value of 4. It will attempt to go to the left-hand side of N4, but there's none. And then it goes back to N4, so it will store a 4 at this point. Then it will try to go to the right-hand side of N4, which is also missing. So now N4 is completely done because it has traversed the left-hand side itself and also the right-hand side. So when N4 is done, it will go back to N2. And there's nothing to do with N2 at this point because it is completely done. Now we go back to N1. Okay, so because we just got back from the L branch of N1 back to N1, so now we process N1, and array would store 5 into the array. Is that okay? And then after that, we'll try to process the right-hand side of N1, which does exist. So it is N3. When we get to N3, we ask N3, do you have your own left-hand side? N3 says, yep, I do have a left-hand side, which is N5. We get to N5, and we ask the question, do you have a left-hand side? N5 says, nope, I don't have a left-hand side. Okay, fine, let's figure out what your value is. It is 9, so it stores a 9 into the array A. Then it goes back, then we'll ask N5, do you have a right-hand side? N5 says, I don't have a right-hand side either. So N5 is all done. Then we go from N5 back to N3, and because we're coming back from the L branch and before we're going on to the R branch, this is the time when we process the 10, the value of 10 of N3. So 10 is now stored into the array, and then we attempt to go to the right-hand side of N3. N3 says, I don't have a right-hand side. So N3 is now completely done. So we go from N3 back to N1, and N3 is also completely done because we have just returned from the right-hand side, and that returns to main. And so by the time we get to main, array A is going to have the values 3, 4, 5, 9, and 10 in the array. But the way it's going to be displayed is not going to be like this. You will see the 3, you will see the 4, you will see the 5, but the 9 is going to look like \T, which is the tab character, because 9 is the ASCII code of tab. If you press the tab key on your keyboard, that usually is associated with ASCII 9, which is the tab character. And then the 10 will appear as \N because that is also the ASCII code of the line feed character. So when you print out A or individually or as a string, it will display 3, 4, 5, tab, and new line when the whole thing is done. But the C code does work. Okay, so the point is the C code does work. What your assembly code needs to do is to basically mirror the operation of the C code, and this is how you can debug your assembly code. Is that okay? Are we good so far? Okay. how do we get started with this program? I mean, this program does look kind of difficult, okay? But how do we get started with this one? Obviously, the main, I mean, you have to implement main so that it actually does something, but I'm already giving you the code to initialize the node, so that part is already done. So main itself is not too hard, okay? You do have to implement this subroutine call, but that's about, the most difficult part of main is to implement the traverse call. But when you go to traverse, how do you get started with traverse, in order to debug your program correctly? The first thing is make sure you can check whether the pointer is null or not. Okay, that's the first thing you do. If the pointer is null, so what you do, okay, I'll comment out stuff here just so that you can focus on how to debug, how to implement the program. So first version of your code would take out everything that is complex and just leave this part here. Okay. I would do this as the first version of traverse. Just check whether pointer is null or not. If PTR is non-null, you do have a value. Store that value to the byte that is pointed to by a pointer, that in return is pointed by array, and then advance array by 1. That's all you're going to do. Then you return back to main right away. There's no recursion. So when you're back into main, you can either use the GUI version, or you can also use the command line version of Logisim in order to track, okay, did I just put 1 byte into the array? Did I advance the pointer by 1? Okay, get that done first. Are we good so far? Because it's non-recursive, you're not going to be able to chew up the stack indefinitely, so all the complex problems cannot happen at this point. So you can debug the program, just the way it is. Once that is done, then you can remove, then you can uncomment, these things just one at a time. Okay, I would just kind of uncomment the left-hand side. Oops. Wrong place. And do one recursion just on the left-hand side. So if you implement a program like this, then you do have recursion. And in that case, you would be just traversing the left-hand side. When there's nothing on the left-hand side, then you just go back. So in this case, it will store a 3 first, and then it will store the 5, and it's done. Because it does not attempt to go onto the right-hand side. Is that okay? Are we good? Okay. So if you can get the program to work like this, and it will store the 3 and the 5 into the array, then unleashing or uncommenting the right-hand side is pretty easy, because it looks exactly the same as the first part, except you're accessing the member R instead of the member L. Is that okay? I mean, are we doing okay so far with, in what order should we implement which part of the subroutine? Are we good? Okay. Any questions? Yep.
So when we're initializing the nodes, we're doing that with the code that was in question 3 at the lab, so the statically allocated or something in the. So they're actually going to be inside the program code section of RAM.
Yes. So when you look at the question, okay. So in question 3, the first thing you want to do is to kind of do what I did in class today, to define a bunch of labels for node. So if you are consistent with what I said, what I did today, you would have node underscore value being 0, node underscore L being 1, node underscore R being 2, and then node underscore size being 3. Okay, so you're repeating kind of what I did in class. This chunk of code, which is already written in assembly, you can just copy and paste it, but you don't want this to be preceding the main program. You want to put this kind of at the end first. Okay, so let me show you what I mean by that. Let me put it into, not this one. I will make a new one like this. Okay, So as far as your code is concerned, you just copy and paste this portion. But you don't want this to be the beginning of the whole thing. So you do need the no op d with 0 and main and halt to be the beginning part of your program, because execution starts from location 0. So you don't want to put your node definitions at the beginning. Is that okay? Okay. So now you want to implement your main. And I can even give you this part. Okay, so we'll go ahead and implement main the way it is. Okay, there we go. All right, so when you do main, you have array A, which has a size of 5 bytes. So you would decrement the stack pointer by 5 because of that. Okay. I know there's a faster way to do this, but I'm just emphasizing, kind of what you're doing here. So this is to allocate for array A. And then you do another decrement to allocate for local variable PTR. So now we want to define the names, labels for all of these things. So PTR is what the stack pointer is pointing to, and then A is right after PTR, so A has an offset of 1 from where the stack pointer is pointing to. Is that okay? Okay. And then we say PTR equals A. That is confusing because PTR equals A is not referring to the value of array A. It is referring to the address of array A. Okay. So we are storing the address of array A into the local variable PTR. So the way we do this is LDIA with, okay, this is going to be confusing, but LDIAA. This A refers to array A. This A refers to register A. The assembler would be able to figure this out, okay, because it knows what to expect depending on whether it's the first or the second operand. If you don't want the confusion, you can say, you can turn this one into just array and then spell out array over here. So that's a little bit more clear. You have to add the stack pointer to A, because otherwise it is just a displacement or an offset. You have to add the stack pointer to the offset to get to the address of the local variable. That's your right-hand side on line 37. Now you have to do the left-hand side. So the left-hand side is similar. Okay, you do this. And then, now in your code, I would not use PTR because you cannot define PTR twice, once for main and once for your local subroutine. So I'm going to change PTR to array PTR, okay, array pointer. So this way, when you just copy and paste the code, you won't get into the problem either. So we add AD again. BD. So register B now has the address of array pointer in main. Then we can do a store like that. So these 5 lines of code in assembly from line 14 to line 18 is going to implement line 37 of the main program. Are we doing okay so far with this? Okay, all right, excellent. So line 14 and line 15 are corresponding to the right-hand side. Line 16 and line 17 are corresponding to computing the L value or the location of the left-hand side. And then line 18 just does the store once we have both the L value and the R value. And then the call itself is kind of similar, except this time we have to compute the address of the array pointer. So we have load A with APTR, add AD, and then we push it on the stack. Decrement D, STDA. And then we have to push the address of N1 on the stack. Now this one is a little tricky because we don't talk about global variables too much. So because N1 is a global variable, it is not relative to where the stack pointer is pointing to. N1 as a label really is defined to be the address of the node N1. So that one is super easy. Just say LDIA with N1, and that's all you need to do. Decrement D, STDA. So this is going to push the address of N1 on the stack, and this is pushing the address of APTR on the stack. And then we just do the usual call thing. Okay, so we have decrement D, LDIA dot 5 plus, stda jmpi to traverse. And then when we come back, we increment the stack pointer twice to deallocate the two arguments. And then at this point, we only have the local variables left on the stack. So we have to do, they add up to 6 bytes, so I'm going to do it the quicker way. So LDI is A with 6, add to the stack pointer A. So at this point, the stack pointer should be balanced, should be back to 0, and then the halt instruction is right next to it. So this is your main. So now what is left is really just traverse. Are we okay with this code? I can send this file to you too. I mean, I have not debugged main, okay? So if it does contain a bug, you kind of have to figure that one out. I don't think it has a bug. So let me save it to here as tree main.ttpasm, and then switch back to here. So I'm sending this one too. Hopefully that will help with your homework assignment, because now you can just focus on traverse without having to worry about the main. What is the name of that? Tree main. Yep, there we go. And save. There we go. Are there any questions?
Did you say this was recorded or?
It is still being recorded. I can see OBS from my end.
Just so I can go over it and see.
Yep, well that's the whole point. I mean, I do want you guys to get the files and also get the recording so that you have time to pause, slow down, check it out, to understand the code. Are we good so far, or can I answer any questions at this point? Nope. Okay. So I would just use the C code to help you understand what you should be expecting from the assembly code. So that means, if you are implementing the C code in steps, as I suggested, then you will go into the C code and actually change the C code to the point where it is matching the assembly code that you're implementing. That way you can actually check to see whether your assembly code is doing what it is supposed to. Are we good so far? So make use of the C code, okay? I made that C code so that you have a chance, you have a way to check the behavior of the assembly code, compare that against what the C code is doing. But you do need to use a debugger to help in this process. Are we good? Okay. I'm going to turn off the recorder if there are no other questions.